All right, so any questions? This is your last chance. Well, I have office hours till 1 today, but that's probably your last chance because I'm probably not going to be able to answer a lot of emails tonight.
I'm pretty sure like whatever happened with my ODP was probably because it's just not. I don't know what I'm trying to. I know what I'm trying to say. I'm having trouble saying it. I think I figured it out.
Okay, cool.
So we'll see.
Awesome. Sounds good. Yeah.
So for PA1, there is a case that you said that not to worry about, like when you say the command I ha ha ha, or no, sorry, I 25 ha ha ha.
Right.
So let's say we said I ha 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 25. You should not parse that file, right?
Yeah, that should say it's an error. Right, it should be I space followed by a number. But if there's extra stuff after that number, I'm not going to worry about that. Yeah.
For the delete function of programming assignments 1, when we delete a node, is there like a data value you want us to reset data to, or do you just leave it as is and then take it out of the list?
It's a good question. For the assignment, you can leave it as is. All you got to do is set that valid bit to 0 and remove, the links in the list so it doesn't point to it. But it's a really interesting question. When we actually implement a linked list and we're not using our own array, we're using system memory, and we free a node, what happens to the data value that was in there? Typically, nothing. Typically, it's unchanged. Which means if you delete something from your linked list and that something had, some piece of critical information in there, it might still be floating around in the memory, and it's no longer memory that's associated to you, and it may or may not get initialized when somebody else allocates that. So that's an interesting issue to think about.
And that's why we get those weird numbers and memories.
That's why you get those weird numbers in memory sometimes. It's just junk stuff that's sitting there.
Can you use Malloc and free it? Does it reset it to something? Or does
Malloc will not initialize. Free might.
Yeah, but when you Malloc the data and you use it, and then when you're done with it and you want to delete it or whatever, when you free it, does it do anything with that?
I don't know. That's not part of the official definition of free, at least as well as I know it. I would guess that maybe that happens, but that's a performance issue. And yeah, so I don't think that it does anything, but it would be an interesting experiment to Malloc a block of memory, throw some data in it, free it, and then Malloc until you get that block back, see if the data's still in there. I suspect in a simpler time, the answer would be yes. I don't know if that's something that is automatically wiped now or not. My suspicions kind of know, but I really don't know.
When you're deleting that node, the order in which you do the valid and changing where the previous node is pointing to, that order doesn't really matter.
The only thing that matters is you want to make sure that you can adjust the previous node to point to the following node, right? So you can either set that previous node first. All right, let's do some pictures because this will come up in a bit. So we want to delete this node, right? The important thing is to take this and change it to point over here. Now there's a few ways to do that. Before you remove this node, right, you can change this to point wherever this thing is pointing. Or you can take where this thing is pointing and save that in another variable and then set this equal to that variable and so on. But here's the important thing, and it's not going to matter for PA1, but it will matter for PA2. When we call release node, this block effectively no longer exists, right? And we should not do anything with this block if the valid bit is 0, which is what happens when we release it. So if you were going to say previous next is equal to next next, you've got to do that before you call release node, right? Because when we're doing this with actual dynamic memory, once we release this node, this value could change immediately. And if we try to set previous next equal to this next, we could get junk, right? So other than that, no, the order shouldn't matter.
But then also when you delete, so like the only thing when you delete a node that's changing is that you're changing the value to 0, and then the direction is pointing to whatever is the next node. But you're still leaving next and the data value in that node, and even the next value is taken.
Correct, yeah. And if you want to change them, right, if you want to sell your software at a premium and say it's secure, right, you could write a 0 into there or something. Get some. Right, so this happens when you delete a file, right? And most people know this, but certainly in the 80s, most people did not know this. When you delete a file, what happens to the contents of the file? Pretty much nothing. It's still sitting on your drive, right? This is why you can undelete, because all you have to do is figure out where the file was stored and then put it back into a file, right? So I ran contra Oliver North, deleted all of his emails, but he didn't scrub them, he just deleted them. And it was very easy to get them back and figure out what he deleted. So if you don't want that to happen, before you delete the file, you overwrite it, right? You throw in a bunch of gibberish, right? And then you delete the file, and now if you figure out where the file was stored, the original contents isn't there. Except, of course, when you write gibberish into a magnetic medium, you don't actually obliterate what was there. You add to it, and if you're really good, you can figure out what was originally there based on what was written. So unless you're writing random information, or you write several different patterns that alternate the ones and zeros, you might still be able to recover what was deleted. So all good stuff if you do a computer security course. Lots of interesting details. All right, other questions? Good to go? All right, so let me show you what PA1 should look like. Doesn't have to look exactly like this, right? Just general behavior of this. So I say main and I just get a prompt, right, telling me to do something. You can be a little more friendly if you want. If I type something that it doesn't understand, it will give me a brief synopsis of how to execute this program. So insert a number, print, search for a number, delete a number, exit the program. So if I say print, there's nothing in my list, so I get an empty output. If I insert a number like 10 and I say print, I get a 10. If I insert a 20, it tells me success, and if I print, I've got a 10 and a 20. Okay. Am I done testing my insert function? No. Go ahead.
Is it supposed to print a 1 or a 0?
It's supposed to say success. Well, what did I say? So main program should print out success or a node already in list. All right. So this looks like it's working. We're far from done. Right? Why? Well, first of all, what happens if we try to insert a node that's already in there? Node already in list. Okay, that's good. Let's insert a 30 and print. Really looks like it's working now. Are we done? No. No. Yeah, we inserted these things in order. How do we know it's actually sorting? So let's insert a 15 and print. Hey, it's actually inserting. That's good. Let's try inserting in the very beginning. Right? Edge case. Insert a 5. That looks good. Let's insert to the very end. We've technically already done that, but let's make really sure. Okay, now it's looking a little more like the insert function actually is working. But let's check if we try to insert the first node or we try to insert the last node, make sure it finds those. If you have a while loop and you're kicking out one spot too early, right, and you try to insert 40 again, it might not notice that 40 is already in there. So that's another edge case to check. Same with searches. Let's search for something in the middle, search for something in the beginning, search for the end, search for something that should be before the first node, search for something that should be after the last node, search for something that should be in the middle, right? So I've already done a dozen test cases, right? And we're really just doing insert and search and print. All right, what about deleting? So delete something from the middle, make sure that works. Delete the first node, make sure that works. Delete the last node, make sure that works. Make sure that whatever node you deleted, it doesn't think is still in the list. And try deleting those again and make sure that it doesn't, make sure it's paying attention to the valid flag basically. Because chances are those numbers are still in your array, but the valid flag on each of those entries is set to 0 and they're not linked to through the list. So this will catch any functional errors in how you're implementing these things. What else should we try? Delete the first node, delete the last node, delete down to where there's a single node, delete the last node so your list is empty again. And then try deleting again. And try searching. And make sure that as you've deleted everything and you're back to an empty list, you're really back to the same empty list you started with. Sometimes you delete the 3 nodes you inserted, and when you say print, the list looks empty, but if you try to search for something, it does something weird, right? So bring it back down to 0. Search for the data value that you happen to know is in your Sentinel node. Make sure it doesn't show up. I've got a 42 in my Sentinel node's data. It should not be part of the list. So search doesn't bring it up. Trying to delete it doesn't succeed. Inserting it will succeed. Deleting it from there will succeed. All right, try some errors. So insert something that's not a number, insert without a number, search without a number, delete without a number, and so on.
Do you want us at the beginning in the first program, do you want us to have this little help?
Yeah, that's fine.
Right away?
You don't have to, but it's fine. It's probably better to print out that help message up front because it's otherwise you don't know what to do. Except I'll have done this 60 times by the end of the weekend. All right, makes sense? So I'm not worried about, you know, insert 20, 30. Just see the insert 20. I don't care about the extra stuff after the command. Because chances are you're just going to use scanf. You're going to look for an I followed by a number. And if you get that back, you're good to go.
Did you try typing an I and then 20 without a space?
That should work.
Yeah, it was working for me. I was kind of surprised.
Yeah, if you do scanf I space %D, the space is kind of optional. It's one of the sort of weird but good things about scanf. Spaces are treated differently.
So if I do like in quotes %, star C, star num I, or %I, the space even though it doesn't matter?
Doesn't seem to matter, no.
Okay.
If I had one ignored it, it would. If you had a space and you ignored that in your actual scanf, they'd break. But the space probably just gets ignored otherwise.
I think if you scan for a %C, %S without a space, and you put a space in when you're typing in, I think it'll still scan. I'm not positive, but I'm pretty sure.
Wait, so how do I think my program can do what you did, like the key and some bigger stuff. So then it's not gonna program picks it up as a number. How do you make it that?
So when you do an scanf, so So you got some kind of string, you got a search pattern. So let's say we're searching for D followed by an integer and the address of a variable you want to plop that value into. As Scanf returns an integer. Okay, this is the number of conversions. The number of things that it converted from one format to another. I'm asking it to convert one thing. Whatever comes after the D, I want it to convert into an integer. That's what %D or %I does. So N should come back to be a 1. So if N equals 1, then we succeeded in converting what came after the D to an integer. But if I type in D space ha ha ha, this N will not be 1. Okay, and this will fail. That'll tell me that I didn't have an integer. Make sense?
Yeah.
All right.
Thank you.
Yep. Yes?
So we don't have to worry about like big integers?
No, I won't put in an integer that blows up. So it'll be between 2 billion and minus 2 billion.
Oh, that's big. I'm pretty sure it just collects negative.
Most likely it will truncate.
When I tried on mine, it just made -1.
So, oh, it was just -1, you're right. Okay. Well, that's kind of cool. Yeah.
Are negative values something you expect us to be able to?
Yes, you should be able to insert negative numbers and they work exactly the same.
Okay.
And if you're using scanf, that's going to happen for free, right? If input contains, D space -17, that'll match this pattern, val will be set equal to -17.
So what would happen if they had like the negative sign but then a space in between the number? Would it fail or would it?
I think that will fail. Let's see, because I'm using exactly an scanf. Yeah. Just like if you have spaces between the 2 and the 5, it's not going to scan as 25, it's going to scan as 2. So this is trying to scan a minus sign as an integer and it's failing.
Will we lose points if, like, when you're grading this, you input the data value that our Sentinel node has, and then it doesn't work?
Yeah, that's definitely something you want to try to manage.
Okay.
And it should happen more or less automatically,
You didn't really handle that, right?
provided you're really consistent about this.
I'm gonna get a little bit of drawing boxes right in this house.
Yeah.
Oh yeah. This is always the node you want to start with, right? This you can keep track of as the node before the node you're looking at, but this is the first node you want to look at, whether you're trying to figure out where to insert, what to delete, whether to search for something, and so on. Always start with the thing pointed to by the Sentinel.
So it should just ignore whatever's in.
So it'll basically ignore the Sentinel. The only thing the Sentinel's doing is giving you something that points to the first data node, so that if you have to remove this, you can change it to point after, and so on. So if you're consistent about that, right, and you happen to have a 42 in here, but you insert a 42, it shouldn't be comparing it to this. It should just start from here and find the right place to insert it. And it might come, right here, for example. Okay, at no point should your functions be doing something like the following. Search for a value. You don't want to just start at the beginning of your array, go from 1 to 100 and search to see if the data value is equal to the number you're looking for. Okay, that's not the idea here. You always want to be working with this linked list structure. Follow the first node, the second node, the third node, and so on and so forth, okay, like the algorithms we've been talking about. You can kind of get there other ways, right? You could technically do a search by saying just go through every element in my array of struct nodes, and if the valid field is 1 and the data value is the number I'm looking for, it's in my list. that'll give you the correct result, but totally the wrong experience, okay? And it's absolutely not going to work in PA2. So you really want to stick to this idea of following nodes, okay? You got a hand up?
Yeah, I'm always confused on using fscanf versus scanf and scanf.
Only use scanf.
Okay.
That's going to be my edict for here, which means you're scanning the contents of a string, okay? Which means that usually you want to do something like an fgets, name of the string, length of the string, and whatever file you're trying to read from, which for us is usually going to be standard in. fscanf is like scanf, but instead of reading from standard in, it reads from a file. But I don't want people using scanf or fscanf in here because it can trip you up so easily, right? Now, I'm not going to take off points if you use it, but if you use it and it trips you up, I'm not going to have a lot of yeah. Right, so this breaks the process of inputting and parsing into two separate pieces. And it means you can input once and you can parse it 5 or 6 or 10 different ways until you find what it is that you're looking for. And then when you're ready for the next line, you go back here and you do an fgets and that reads in the second line. If you do scanf or fscanf, it's ingesting and parsing at the same time. And depending on whether your scan succeeds or fails, affects how much it ingested, right? And so it becomes a sort of multi-fronted problem to debug. So scanf should work for here. Good, other questions?
What would cause, in that example where you have 42 as your sentinel, what sort of thing could cause putting a 42 in failing, or reading what you're reading? What could cause that to fail?
If you simply start with, this is the first node I'm looking at, right? So you have a loop you set next to 0 because that's the first node, and you say if ll bracket next dot data equals 42, and right here it says yes it is, so I'm not going to insert 42.
So that's kind of what the get first function is.
Yeah.
Helping you.
Well, get first.
Kind of.
Yeah. Right. So that was an exercise to work exactly with that concept. And the worst thing is if you say delete 42, and it says, oh, here we go. There's my 42. I'm going to delete it. Right, and you try to change the previous node, which doesn't exist, to point, right, you're going to seg fault.
So when you're deleting or searching, make sure to start at 1 instead of 2.
Yeah. Well, not necessarily 1. Start at the thing that 0 points to. It may not always be index 1. Because you might have deleted, yeah. Tangled knot, and you want a tangled knot, right? You want some test cases where you insert 10, 20, 30, and then delete 20, and then insert 40. And now in your array, you're going to have 10, 40, 20, right? But in your list, it's actually 10, and then you jump down to 20, and then go into the middle to 40, things like that. So you're also welcome to give your executable code to a friend and say, try to break this, right? That's fine. Once you've done this and you think that your code is totally bulletproof, right, is always doing the right thing. If you want somebody else to run it and see if they can break it, I'm fine with that. Right, as long as it's just the executable. And some people have a knack for breaking code. I've got a knack for breaking code, it seems.
Most of the code breaking students.
Yeah, well, I'm good at breaking my own code too. All right, well, let's look at PA2. So keep working on your PA1, right, until it's done or until tomorrow morning at 8 o'clock. Or you can work beyond, right, and take 25 points. But I want to go over PA2 because tomorrow is going to be another one of these kind of open labs. So hopefully people come to that and make good use of the time. But if you don't, I want to go through this before the weekend, right, before Monday. So you have time to start it over the weekend. On PA1, right, make sure you turn in something, okay? Unless you're deliberately, you know, going to wait and turn it in within 48 hours and take a point hit. Make sure you turn in something, right? If there's nothing turned in, it's a 0, okay? I can't give you partial credit for no submission at all. If you turn in something, you've got some piece of it, there's usually partial credit to be had. If you've got your functions working, but your main program is not, that's not a real big problem, right? You need everything to be working in order to get 100%. But this is an exercise on linked lists, data structures. I mostly want to see that your functions are correct and that they work. Okay? The main program is a fair amount of work, right? It's getting input, it's parsing it, it's calling your functions and doing whatever you're supposed to do with the result of those functions. It's not conceptually novel after 224, but it's still a fair amount of work, and it's possible that you run out of time before you've got your main program done. Go ahead and turn in what you have, okay? And if nothing else, write some test cases that you were using to test your functions. Put those in your main program, right? And if you've got pieces of your main program, leave those pieces in there. And you can always put a note on the submission, right, and tell me what's going on, right? I got everything working, but I ran out of time, and here's where my main program is, and so on, right? And the main program is not worth 50% of the points, okay? It's worth, you know, maybe 15, 20% at the most. So, so concentrate on the functions themselves, the linked list behavior, and then the main program after, but turn in whatever you have. All right, the other thing is, I've said you can turn this in late for up to 25, 50 points off, right? 48 hours. You cannot do that once I've graded your assignment. Okay, I don't want to grade your assignment, put the grades in, and then you make some corrections and turn it in again and say, here's my late submission, right? So if you're submitting it just to make sure that it's submitted, but you're planning to resubmit within 48 hours, let me know that in the submission comments, okay? Because I recommend people upload early in case the network goes down, you know, tomorrow morning at 7 or something, right? It's better to have something uploaded. But if that's not your final submission, you're just putting that in as a stopgap, let me know, okay, so that I don't grade it. Once I grade it, that's the final. Make sense? Okay. So PA2. This looks a lot like what you've already seen. This document is almost verbatim the document for PA1. I just made a few changes to it. One of the main changes is this definition of a struct node. So our struct node for PA1 has 3 fields: data, next, and valid. And they're all integers. For PA2, we get rid of the valid flag. We're not going to have to worry about that anymore. But we're going to make this change to the next field. It's no longer going to be an integer. What is it? It's almost a struct node. It's a pointer to a struct node. Okay, and it's not actually an array. It's really just a pointer to another struct node. So our node, our struct node, contains a field that points to another struct node, or possibly to itself. So that's potentially a little quirky to wrap our brains around, but this is going to be what we do the rest of the term.
Is it like an embedded list, sort of?
Sort of, but it's not actually like the nesting dolls kind of thing. But it feels like that. If we had next being a struct node, that would actually be this. You know, there's actually a node inside this node, and there's another node inside that, and that'll actually blow up when you try to compile that, or at least when you try to run it. But this is a pointer to a struct node, so it's a memory address at which we will find a struct node. Okay, so that's one change. The second change is that in our main program, we're going to declare a struct node star list instead of struct node list bracket 100. Okay, list bracket 100 made an array of 100 struct nodes. This is more general. It's just saying this is a pointer to a struct node somewhere. All right, and then the init function, this is the only function whose prototype changes. PA1's init got an array of struct nodes and it did some stuff in there, right? PA2's init doesn't take any arguments, but it returns a struct node pointer. Okay, it returns a pointer to a struct node, which will be the sentinel node of our list. So the pointer returns a pointer to an empty list, which means that there's a sentinel node pointing to null, and there's no other nodes. This is the other change, is that we're using null instead of myNull when we want to say something like there is no next node. We said it's null, N-U-L-L. And null is defined for you in standard IO.H. So we don't define null ourselves. After that, it's business as usual. Add takes a pointer to a struct node and an integer, searches through the list, inserts in the correct spot, returns a value. Print takes a pointer to a struct node, prints out the entries on one line. Delete takes a number and a struct node pointer and deletes it. Search takes a struct node pointer and a search, looks in the list for that number and returns a 1 or a 0. And that's the main routines that your main program is going to use. And your main program is exactly the same. Okay, the description is completely unchanged. And if you wrote your main program the way that I intended you to, which is when you want to delete a node, you call delete. When you want to add a node, you call add. You're not going to have to change your main program at all, other than the declaration of what a struct node is and the way you initialize. So you'll initialize by saying struct node star list equals init instead of struct node list bracket 100 init list. And then everything else is exactly the same, error checking, deliverables, and so on and so forth. So really PA2's look and feel is the same as PA1, but the way we implement it is going to be very different, but really not so different. So in PA1, we have a node that has a data field and a next field, and next is an integer index of the next node. That's PA1. PA2 we've got data and next, but next is a pointer. So it's a struct node star. So what is a struct node star? The star tells us it's a pointer, it's an address in memory, and this tells us what is supposed to be at that address. There's supposed to be a struct node. So if this next field is equal to 100, it means if we look at memory location 100 in memory, there should be a struct node starting at location 100. And so whereas we've been drawing an array and filling in the different fields for PA1, here's what a list might look like in PA2. So we're going to have a sentinel, and we're going to have, let's say, 2 nodes. And let's say we've got a 10 and a 20. All right, let's say this is our memory. And let's say at this random location, 600114 hex, that would be where our sentinel is. So we've got some data value, maybe there's a 42, that's in the first 4 locations. And then in some location after that in memory, probably the next 8 locations, there's going to be some number. Maybe it's 600120. That's a memory address at which we're going to find presumably the second node. So somewhere down here, 600120, we'll find the integer 10, followed by, on our server, 8 bytes of address information. And maybe it's 600700, and somewhere down here at 600700 we find 4 bytes, which has this 20, and then we have null, and null is an address of 0, but we never want to actually code a 0 in there. We want to use NULL because on some other system it could be something different. So use the symbol and it'll change when you recompile on whatever environment you're in. So this is what our memory actually looks like. Okay, it's kind of like our array, except it's not an array that we created. It's the array of bytes that comprise the memory of the computer. And instead of an index into an array, we're actually just using a memory address. So if we go into GDB and we look at this and we see this 600, 700, and we actually examine that memory location with an X command, we'll see a 20 stored there, followed by 8 bytes of 0. So it's almost the same concept as what we were doing in PA1, but we're doing dynamic memory instead of working inside an array. So as we're marching through our list, let's say we've got previous and next. Let's say we're trying to insert a 15. So we're doing our same thing where we've got previous and next, and we're moving down the array. But previous is no longer an integer. It's a pointer to a struct node. And next is also a pointer to a struct node. It's an address in memory where we can find a struct node. So let's say we wanted to delete the 20. So in PA1, where these things were integers, we were saying something like list bracket previous dot next equals list bracket next dot next. Alright, so we're taking what this is pointing to and we're changing it to point to whatever next was pointing to, so that now this points over here. In PA2, previous is pointing to a struct node, so we can refer to the struct node by putting a star in front of previous. That dereferences a pointer. So the node pointed to by previous, and we want its next field, and we want to set that to the node that next points to that thing's next field. Now don't do this mechanically at first. Don't just take this and try to mimic it. Think about what's going on here, right? This is a struct node pointer. Star previous is a struct node. It's this struct node. This struct node dot next, that's this block right here. This is a pointer to a struct node. Star next is actually this struct node. Star next dot next is this field within that struct node. So this is setting this field to have whatever value is stored in this field. And if we actually write the addresses in here, it's basically copying this address into here. So now this is pointing to the 30. Seem doable? So there's a shorthand that you'll see that'll make your life glorious. Let me give you an example of glorious life. Suppose we have a variable temp, which is pointing to this node right here. And we want to get to not the following node's data field, but the data field that comes 2 spots after it. Let me just call that X. We need to follow 2 of these pointers, right? So if we say take the thing pointed to by temp and look at its next field, this corresponds to this node, right? It's the address of that node. If we put a star in front of that, now we're actually referring to this node, not a pointer to it, but the actual node. And if we take the next field of that, that's the address of this node. And if we take the thing that that is pointing to, that's actually this node itself. And if we pick off the data field, that's the X.
That's inception.
That's what?
That's inception.
Yeah, it's inception, yes. We don't want to go there, right? This is really, really error prone and impossible to read and impossible to edit. So we have a shorthand. So in general, the thing pointed to by something dot field can be written pointer arrow field. So we make an arrow out of a dash and a greater than sign. And this means take the thing that pointer points to and pull off the field, right? Whatever this field name is. So it does the same thing as dereferencing the pointer and grabbing a field. Which means that with this notation, if we say temp arrow next, right? This is the next field within the thing pointed to by temp. This is the address of this following node. And if we say take the thing that points to and pull off the next field, that's the address of this node. And if we say take the thing that that node points to and pull off the data field, we just have to write this. That gets us to the X. And it feels very comfortable after a while because we're saying take temp, take the next thing, pull off the data piece. Right? So this notation will make your life a whole lot easier than trying to do these dereferencings. But when you're trying to figure this out, just come back to this, right? This is what the arrow means. The thing pointed to by this, grab that field. But in a few weeks, we're going to be writing these kinds of things all over the place, and it's going to be really fun. Because it gives us a convenient way to sort of grab hold of these structures. All right, so PA2, you're going to have 2 weeks to do it, right? So you've got 15 days from today, actually. And you want to start this as soon as possible, but it probably will not take you 2 weeks, okay? It's going to be easier in most ways than PA1. In the sense that if you've succeeded in at least getting the basics down for PA1, PA2 is a very simple modification. But once you've got PA2 working, right, you're embedding yourself in a language, in a concept base that will let us do everything else in this course. Okay, because everything we do in here, all the data structures we talk about and implement are going to be basically manipulating the contents of memory. And most of the time that means defining a structure that includes pointers to other structures, possibly pointers to its own structure. And once we're fluent in that, we can start spinning out all kinds of structures, graphs, trees, tries, all sorts of good things.
Compared to PA1's form, is this more like, it feels like it's less secure, like from like buffer overflows, things like that? And, like, breaking with types?
So we're tinkering with main memory, right? And it's relatively easy. If something goes wrong, it's going to blow up more quickly in PA2, right? In PA1, if you look at index 10, because the data value is 10 and you use data instead of next, right? You'll get weird answers, but probably you'll survive. In here, if you have something that's not a memory address and you try to use it as a memory address, it's probably going to blow up. So that's one sort of security-ish kind of. But the other thing is what we talked about before as far as freeing memory, leaving data laying around memory. But let's talk about that next. So when you're creating a node, right, and the first time you're going to do that is in your init function where you create the sentinel node. In PA1, we called getNode. And getNode found a spot in our array where we could store a node, right? How do we do that in PA2? How do we find a location of memory where we can store a node? Malloc. So do you touch on Malloc in 121? A little bit?
This is not just structures talk.
Okay. So Malloc, it comes from standard lib, well, its definition comes from standard lib.h. And you can say, yeah, so we can say Malloc something, and this will return an address in memory where we have this many bytes available. So if we want to create a new struct node, we need to know how many bytes it needs. Let's say it needs 32 bytes. We could call Malloc 32, and it will return an address in memory, right, a pointer to a struct node. It won't load any values into that struct node, but it'll give us a block of memory in which we can store a struct node.
So that's where you use size of it.
So we don't know if it takes 32 or not, so we can use the size of struct node. And based on what system you're running on, a struct node might need 12 bytes, it might need 16, it might need 20, it might need 32. So don't hardwire magic numbers, call size of struct node, the compiler will replace that with the size of a struct node. And so Malloc gives us an address, and we can use that address to point to a node. And so if this was, you know, struct node star temp, and we want to set the temp field's data to be 42, we just do that, right? Which is the same thing as saying take the thing pointed to by temp, look at its data field, set that to 42. And if it's a sentinel node, what do we set next equal to? Set it to null. Okay, what if there's no memory available on the computer and we try to malloc space for a struct node and there's not enough memory available, what do you think malloc's going to return to us? It's going to return null, right? So if we're comparing it to null and we see that they're equal, we know we're out of memory. Okay, so the same thing that we did with our get node, it returned my null if it was out of memory. There was no space left in the array. And the last thing is free. Free takes the place of release node. So if temp was something that I malloced, if I say free temp, that memory goes back into the pool of available memory. And you always want to free stuff after you're done using it if you malloced it.
Because you don't get a memory leak.
So you don't get a memory leak. Otherwise, the longer your program runs, the more memory it chews up. And eventually there's no memory left on the system. All right, so that's the really quick 25-minute rundown of the rest of the course, basically, with PA2 in particular. So we'll talk about this a lot more next week. Come tomorrow if you want to work on code, ask questions, go over things, and so on and so forth. Otherwise, I will see you on Monday.
Tomorrow, you know, comments, ask questions, make sure you have the right idea, all that.